So far, in the short course, we have formed our solar system. We have formed Earth. This morning we talked about what was the early environment like, why was Earth habitable. Stefan, talked a lot about our evidence for early life, so really hopefully convincing all of us that there was life around during the early Earth. So now my job is to try to kill it all off again. So I'm going to be talking about meteorite impacts and their consequences for life. And one thing I want to stress is that, you've got the impact and the impact site itself, right? And if you have a big enough impact, right, you destroy a lot of material, you're melting it, you're vaporizing it. So certainly that would be disastrous for life right there. But actually what's going to kill life on a more global scale is the impact-initiated environmental changes that then lead to mass extinctions or at least mass die-offs. So that's what I'll be talking about here. So first I'm going to focus on the meteorite impact flux through time. So how do we know that there were meteorite impacts and how do we know how it changed through time? And then I'm going to spend quite a bit of time on the KPG impact. So the KPG impact at the Chicxulub, or the Chicxulub impact, is really important. Everyone knows it because it led to the extinction of the dinosaurs. So because of this, it has really been extensively studied and has really allowed for unparalleled insights into what meteorite impacts do to the environment and to life. So we're going to look at this as a case study and then move on into deep time. So first I'm going to talk about Archean impact events. This is where we actually have a rock record, and so we can study some of the effects on the environment and on life. And then lastly, I'm going to go even further back in time here into the Hadean, and I'm going to talk about impacts and the origin of life. So when we think about meteorite impacts, first thing we think of is craters, right? I'm sure everyone here has seen a picture of the meteor crater right over here, really beautifully preserved, but there's like many other ones, like this one, the Swain crater in South Africa. These features are, very attractive, these beautiful circular craters. You've got the crater rim. So that's the first thing we go to. And there's these beautiful examples, but overall on Earth, actually more than 200 impact craters have been identified. So the largest being the Fredefort crater, over here, so that's over 250 kilometers in diameter. And then the most famous one, again, is the Chicxulub impact, which is right over here on the Yucatan Peninsula. So again, we have identified over 200 craters at this point, but the cratering record on Earth is really incomplete. So the first thing is that a lot of craters are lost. When we look at the record here, they are on continental crust, so we've got weathering and erosion, so material gets lost. And then another feature that you probably notice on this map is that we're not really showing any impact craters here on oceanic crust. So this is because, as Stefan was mentioning earlier, right, our planet is really active. We've got plate tectonics, and we've got this oceanic crust which tends to get subducted within about 200 million years, and then that material is lost. So there's a lot of surface recycling, and because of that, we are missing a lot of the impact record here. And then the last thing that we have to be concerned about is the geographic bias. Where are we going to find impact craters? Well, we're going to find them where we are looking for them. And that's mostly going to be, in North America, in Europe. But when you look at other places where less of this research is happening, there's just fewer craters, which probably is not a reflection of there being fewer impact events recorded, but more likely something relating to, where research is actually happening. So besides the craters, what else can we look for to identify impact events? So there's, of course, these characteristic proximal impactites. So that includes impact breccias, like you're seeing over here, or swavites, which are basically breccias that have a lot of melt associated with it. Then we've got these shatter cones that form, from the impact you initiate like these really strong seismic waves that are shattering kind of the basement and leave these really characteristic structures behind. And then we've got shocked zircons. So I was mentioning earlier already, right? When we have these really strong pressure waves going through, you're really deforming the crystal lattice, forming these planar deformation features, which can be identified in zircons. Now, as we go further away from the impact site, so more than 2.5 crater diameters away, we start getting into the more distal impactites or distal ejecta. So that includes tektites, which are basically kind of glass fragments. So it's basically melt sort of being splashed out. So you kind of see this teardrop pattern here. And as you go even further away, so more than, in some cases, especially once you're more than 10 crater diameters away, you start seeing more microcrystites and microtectites. So these are just like these really small sand-sized droplets that are either from like the melt that's being ejected out or from rock vapor condensates. So how does that happen with the rock vapor condensates? Because this is something I'll be talking about a lot more when I talk about the Archean. So when you have an impact hitting Earth, right? So the bolide, so the impact itself is going to vaporize. A lot of the target rock is going to vaporize as well. And that's going to form this rock vapor cloud that's going to expand away from the crater side at really insane speeds, 19 kilometers per second. So this is insanely fast. So it forms a rock vapor cloud, and you can imagine like a rain cloud, right, in the sky. It's water vapor. Eventually it's going to condense and you have, water droplets coming down. So imagine instead of water raining down, you've got like silicate melt or like little spherules raining out. So that's what we find in the rocks as well. So there's a lot of sightings of these distal impact deposits. In many cases, we don't know where the crater was. We just know that there was some kind of impact event where we formed these spherules. These have been confirmed with iridium anomaly, extraterrestrial chromium isotope signature. So we know for sure, and everyone agrees that these are from meteorite impact events, but we don't know where the crater is. So the crater is long gone, and an impact might have happened on the other side of the globe. So I'm going to pass around the sample that we are looking at already last night. So this is one of the Archean impact spheral layers. So this one is 3.24 billion years old, and you can see these sand-sized spherules. And I think while you're looking at it, you can get the sense how hard it is to identify these. So spherules, this is a really thick impact layer, right? This was a massive impact. So the bolide, the impactor, was between 40 to 70 kilometers in diameter. Huge, right? But it's going to leave behind a layer that's about this thick. So it's incredibly easy to miss these impact event deposits. So it requires a lot of really detailed and careful field work to find evidence for these impact events. But people have tried for a long time, and between like all these different impactites, whether proximal or distal, as we go in deeper down into Earth history, we find a whole bunch of impact events. Especially here when you look into the early Earth, so anything Archean, so older than 2.5. This is where we found a bunch of these spheral beds. The impact events have been confirmed with iridium anomalies, PGE anomalies, chromium isotopes, and all of that. But you can see here for these Archean, so the early Earth impact events, that the proposed source crater is really unknown. It's all gone. It's just not preserved anymore. So this gives us some idea about the impact history on Earth, but it's not giving us a complete picture, for the reasons that I was citing earlier. So another way we can kind of reconstruct the impact flux through time is by looking at the moon. So the moon, has been our companion for a really long time, and it's also been hit frequently by meteorites. The one adjustment that we do need to make is that because Earth is bigger, it has a bigger gravitational pull, so we're going to see about 20 times more impacts on Earth than we do see on the moon. So the moon impact record is really gorgeous. You see it's just like covered with craters, and people have done crater counts and like reconstructed the timeline here. And that's really helped us kind of think about the impact flux through time, especially during the time that we do not have sedimentary rocks preserved. One quick side note, so based on that, we get this sort of impact curve here that's like rapidly declining. And for a long time, there was the idea of a late heavy bombardment, right? That around 3.9 billion years ago, there was suddenly a pickup in the impact flux. And we have a lot of more meteorites hitting Earth. But I think that researchers have largely moved away from that. So over the last couple of years, right, there's been an idea that, this supposed increase in impact flux 3.9 billion years ago may have been an artifact of sampling bias, right? So, you go to the moon, you're on Apollo, you pick up your rocks. Either you are sampling many different impacts, but what might have actually happened here is that the same impact was sampled over and over again. And there's another issue here in terms of age resetting of the argon-argon ages. So, from people that work on this, and I don't personally work on this, but when I talk to people, it seems like people don't believe in the late heavy bombardment anymore. All right, so putting all of this together, the impact flux models vary here, just like 3 examples of it. So we are looking here at Earth history, 4.6 billion years of Earth history, and here the impact rate relative to today. And you can see that early on during the Hadean, the impact flux was just way, way higher than today. And then there was a decline in impact rate. So the black line here is kind of the typical impact flux from Neukomm et al. But because of the increasing evidence for meteorite impacts on Earth based on the spheral beds, there have been some adjustments to it. So you can see here the late heavy Boardman again with a question mark. But there's this cluster of Paleocene impact events and Neocene impact events, which these clusters could either be real. So then maybe you have a more rapid decline and kind of like these little clusters where you kind of see an increase in the impact rate today, or it could be because our Archean rock record is really incomplete, so it might not truly be clustering. It might just be sampling bias, but it would still indicate a higher impact flux. So maybe it was just higher and kind of declined more gradually through time. Now, this is really important when you think about it, in the context of life. And there's kind of this, this problem there, right? Because we think of life as being like this fragile, beautiful thing, right? And of impacts as being so disastrous, and destroying everything on Earth. So, when we look at the evolution of life here, a lot of people believe that life originated, 3.8 billion years ago, maybe earlier. I was mentioning earlier, there's some molecular clock estimates that suggest that life might have originated as early as like 4.2 billion years ago. So again, this is really in stark contrast to this high impact flux, which might have really affected the evolution of life. And I was saying earlier, that's like really one of the few things we can all agree on, right? That the impact flux was higher during the early Earth. So, this talk is going to be more of a geological perspective on this because I'm a geologist. So, when we want to study the effect of these impact events, we have to look at the sedimentary rock record. And you can see that we lose the sedimentary rock record about 3.8 billion years ago, right? Like during the time where the life might have originated. However, we do have like a whole bunch of impact events, about 15, that are preserved in Archean rocks at a time where we also just had this really simple life, the bacteria in Archaea. So these actually provide a really nice avenue to kind of see, okay, these giant impact events, like how did they affect the early evolution of life? So to do that, let's think a little bit more about the consequences of these impact events. So this is a famous plot from Pirazzo and Artemeva in 2012. And here you can see kind of the diameter of the bolide, of the impactor, and how that kind of translates to impact energy here. And what I want to just highlight is that the energy does not directly scale with the diameter, right? It more so scales with the mass. So if you double the diameter, the mass actually increases much more, so impact energy is much higher. So when we look at small impacts, so anything less than 30 meters, so that's something maybe like the Chelyabinsk impactor that we heard about, meteor that we heard about yesterday, those might not even make it to the surface of the Earth, right? So there's going to be an air bust in the upper atmosphere, and we don't really expect significant ground damage. Now, as we go to bigger impact events here, so for example, the Tunguska impact event that happened in Russia, so for those, we have got an air bust in the lower atmosphere, and that might cause, some damage, but or some like more local damage, but not something we really expect to be global in consequence. Now, as we get even bigger, so when you have impactors 100 meters to a kilometer in diameter, right, there's going to be some regional effects. You might initiate a tsunami and damage to shorelines and all of that, but it's not necessarily going to lead to global extinction. So it's really the bigger impact events here. So 1 kilometer to 10 kilometers is where you start really seeing global catastrophes because you're putting so much dust into the atmosphere, so you're really changing the climate and all of that. And of course, 10 kilometers or bigger, so the KPG impactor was about 10 kilometers in diameter. That's where there's really strong possibility of mass extinction. So let's kind of think about the consequences a little bit more and with a size comparison. So we've already heard about Bennu, which was visited by OSIRIS-REx for a sample return mission. So Bennu is about 500 meters in diameter. So, you know, it's sizable. There's a chance of 1 in 2,700, I think, of it impacting Earth about 150 years into the future. And there was just a paper recently, a few weeks ago, where they modeled what would be the effect of this type of impact event. And basically what they're finding is that, you know, you put so much dust into the atmosphere, you would decrease the surface temperature by 4 degrees Celsius. And because of the darkness, you're blocking photosynthesis, that there might be a reduction in primary productivity by about 30%. So half a kilometer, right, would be really disastrous to us, and I think a lot of humans would die essentially, you know, from starvation. So Bennu is cute, right? Let's talk about some real stuff here. So this is the Chicxulub bolide, which was about 10 kilometers in diameter, really quite sizable. This is the size where we really start expecting more global extinction. And here, and I talk about this in much more detail, but we see the extinction of 60 to 80% of animal species. So really enormous, but still quite cute. Because we go into the Archean, and then we talk much bigger. So I'll be talking a little bit about the S2 impact that happened 3.26 billion years ago. So this one was about 40 to 60 kilometers in diameter. Again, really what we need to be thinking about is mass. So in terms of mass, it was 50 to 200 times bigger than the Chicxulub bolide. So you can expect the environmental consequences to be much more disastrous. And then, you know, Hadean, yeah, lost cause fast, you know. It's really dramatic. But, you know, one thing that we always want to keep in mind is that, you know, the effects of an impact on life depend on several factors. So depending on, you know, what is the size, what's the type and the speed of the impactor, the environmental consequences will vary, right? The location of the impact is important. So if you're hitting the ocean, you're gonna release a massive tsunami. If you're on land, maybe not so much. You might still like have the earthquakes triggering tsunamis, but it might not be as disastrous. Of course, it also depends on the environmental conditions, right? So there's, when you have a giant impact, you form this melt pool and you might see a lot of outgassing, let's say outgassing of CO2. Now, if you're hitting during the Archean and your atmosphere is super rich in CO2 in comparison today, it's not gonna make much of a difference, right, in comparison to if it happened today. And then lastly, the question is like what types of life are present and what do they need to survive? So, and to give a lot of it away is that, you know, complex life, if it's being hit, it's gonna be much harder for complex life to kind of recuperate and regrow. Versus if you have more simple life, like you might have had during the Archean, you know, life might be able to actually kind of kick back in quite rapidly. So with that being said, there's the famous kill curve, so percent species killed versus crater diameter. So people have proposed that to kind of like get an idea of like each impact, what would it look like, how many species would you kill. But I would argue that you kind of need a different curve for each age and each environmental condition and each impact location and all of that. So it's not so straightforward, right? It's a little more nuanced when we think about meteorite impacts. So let's first talk about the famous KPG impact, because this is where most of the work has been done. So we have learned a lot that we can then kind of use to understand the early Earth impacts a little bit better. So what happened at the KPG extinction? So it's one of the really big mass extinctions in Earth history. As you can see over here, we see this really big dip in the number of marine families. It happened about 66 million years ago, and it was a really rapid extinction event within less than 10,000 years. And the recovery took quite a while, like more than like 500,000 years. So again, overall, 60 to 80% of all enemy species like went extinct. And that of course includes the all non-avian dinosaurs and most tetrapods that weighed more than 25 kilograms. So it was a really dramatic event in Earth history. However, you know, we don't want to be so bleak. There are also positive consequences, right? Because, you know, this allowed other organisms to take the place of like the dinosaurs, for example. And there's a lot of species diversification during the Paleogene period. So people or paleontologists have recognized this mass extinction event for quite a while, and there was for many years there was a big debate about what caused it, right? We have got, you know, volcanism, impacts, you know, whatnot. And then it was really I think in the 1980s that people, the Alvarez father and son, identified an iridium anomaly associated with the extinction event, which was sort of the first clue that this might have been from a giant impact. And then in the 1990s, the crater was discovered. So the Chicxulub crater here on the Yucatan Peninsula, so it's a little hidden. It's not quite obvious when you look straight down, but it's very clear that there's this giant crater there that's 180 kilometers in diameter, and the bolide is thought to have been between about 10 to 15 kilometers wide. So really quite a big impact event. So now, as I was saying earlier, right, you don't only have the proximal impactites, but you also see a lot of material much further out. So in this diagram here, so again, the impact craters here, so you see some of the proximal deposits here, but you find evidence for this impact event all over the globe, everywhere. And it's really beautiful because it's such a beautiful marker horizon that you can correlate on a global scale. But as dramatic as it is, as you go further away, oftentimes the KPG boundary deposit is really thin, maybe about a centimeter or so. So it's small, but it's really disastrous consequences. And this is a really great study, if anyone's interested in it, showed that out from 2010, where they really summarized some of the effects of the KPG impact really nicely. And essentially what you see is this massive extinction event here that's associated with a negative shift in the carbon isotopes, which is basically thought to represent the collapse of primary productivity and the biological pump in the oceans. That, of course, would have a lot of consequences, because if you collapse primary productivity, it's not only the algae that die, but also, fish that feed on the algae and all of that. Of course, once you have the impact, you've got these opportunists that are able to radiate right after the impact event, kind of these disaster taxa like ferns that can really flourish after. And then, of course, right, if you're vacating a lot of these niches, that will allow for radiation of other species. So I was mentioning already earlier that of course, a lot of things die right where the crater is, but it's on the global scale that we are seeing this extinction. So, what are some of these environmental consequences? So, the first thing is that you hit Earth. In this case, it was in a shallow water environment on a carbonate platform, and that has several consequences. So, firstly, you are going to initiate a giant tsunami that's gonna kind of migrate across the globe. It wasn't quite in the deep ocean, then it would have been much worse. So maybe we are lucky in this sense. But you see evidence for the tsunami, all over Mexico and southern US. And then on top of that, besides the tsunami, you are initiating huge seismic waves, right? So earthquakes magnitude 11. So those are going to shake up things globally. Well, mostly really close by, but there's on the antipodes, so on the other side of the globe, the waves might converge again and cause some stronger shaking. But this is going to also cause some impact-initiated slumping. So if you have some kind of shelf with lots of sediment, you kind of shake it, it might dewater, and sediments might start flowing down the slope. So we can sort of see this happening. So when you look at the sedimentary deposits, from very proximal to more distal, if you're very proximal, there's this huge graded clastic unit. So you see here many tens of meters. And then even as you're going further away towards the proximal areas, here still Northeast South Africa, Mexico, you see these high energy clastic units that are potentially related to tsunami events. People have, of course, modeled this. So here you can see models of the tsunami wave height. So the dark red here is about 10 meters. And you can see, so it hit here and the tsunami wave would have reached as far away as Australia. But again, it hit a shallow carbonate platform, right, in a sort of protected area, right, because it's kind of enveloped here by continental crust. So the tsunami wasn't as bad as it could have been. So in that sense, it hit a carbonate platform, shallow water. Maybe that's good for us. But not exactly, because the problem is that when you hit a carbonate platform, you are just ejecting or releasing a lot of climatically active gases. Right, so the impact releases large quantities of water, dust, and climate-forcing gases, and that really dramatically altered the climatic system. So, imagine you're ejecting a lot of dust that's going to start blocking sunlight, right? All the sulfur that's going to be released is going to transform into sulfate aerosols, and those are going to reflect sunlight as well. And then you have all of that soot going into the atmosphere. So you kind of see that here it's all being ejected. And in this diagram here, you're looking at radiation, like against time. And you can see here with the impact events how the radiation is getting close to zero with like all of these things combined. And it would take a few years kind of to recover the system. So how much sulfur and carbon was ejected into the atmosphere is really difficult to constrain. But there's some ideas that, hundreds of gigatons might have been emitted. So people have looked at this and tried to model it to see, well, how big would the effects be, right? So you have darkness, but you also have the impact winter. And here we're looking at the change in surface temperature, and you can see that some estimates suggest that it might have been more than 20 degrees Celsius of cooling for several years. So this would, of course, been like really dramatic. We can see this in the modeling, but we can actually look at that also in the rock record. This is an organic paleothermometer where you can really clearly see here in the surface temperature how there's a sharp drop in surface temperature. So between the darkness and the drop in temperature, this would have been really disastrous for a lot of life. One quick note, because for a couple of years there was kind of this debate, was it really the impact that caused the extinction, or was it the eruption of the Deccan traps? So the Deccan traps here are in India, and it's just this huge amount of flood basalt that kind of erupted at the surface. And that would have been really a strong stressor on the biosphere, right? So people have gone in and done really precise dating to see, okay, does the eruption of the Deccan traps really correlate directly with the KPG boundary? And could that be our major cause for the mass extinction? Well, so the extinction is happening here, and it looks like, when you look at the dating, that the Deccan traps erupted in several pulses. And some of it preceding the impact event, but it probably just wasn't enough to cause mass extinction. So it might have been global warming by maybe 2 degrees Celsius, which, we hope to avoid in the upcoming future, but it's nowhere near as dramatic as if you have the impact that you then drop the temperature by 20 degrees Celsius or more. So we don't think the Deccan traps was the cause of the mass extinction, but it's something that would have been an additional stressor, which might have made the biosphere more susceptible. And then another thing that we have to think about, and this is really the case here because, again, we hit that carbonate platform, we're releasing so much sulfur, where you form the sulfate aerosols, and as those rain out, they're going to start acidifying the oceans. So here we're looking at the aragonite saturation state before the impact and after, and you can see that's gone way down. So might have been a change in pH. It's not too bad. I think it's like about 0.4 change in pH. But if you're an organism that relies on a carbonate skeleton or something, and you live in the shallow water, you might have been severely affected. Putting all of that together, right? There's a timeline. Not everything happens at once. Some things happen earlier and some happen later, right? You have got the blast and local ignition, the fireball that are really only. Oh, this shifted, sorry. So this is supposed to be ours. That could happen really early on. The earthquakes and especially the tsunami, depending on how far the waves go, right? That can go on for hours and maybe even days. The dust in the atmosphere and the global cooling, from the sulfate aerosols are going to last for a few years. And then the acid rain. And then because you're also emitting carbon from the carbonate platform, there's going to be some global warming kind of longer term, but it probably was not very strong. So it probably didn't affect things too much. So now, what's killing things? Right, so we know there's an impact, and there's different proposed killing mechanisms. So there's, the darkness. So if you're a photosynthesizer, that would kind of suck. There's the impact winter, ocean acidification, heavy metal poisoning. And one thing I want you to take away from this is that, different organisms are going to be reacting differently to these different mechanisms. So again, if you're a photosynthesizer, the darkness is going to be problematic. But if you live deeper in the water column, right, you might not care that much, right? You don't depend on light, right? Ocean acidification, well, again, if you're like a calcifying organism, this will be a problem, especially if you're in the shallow water column. If you're deeper in the ocean, it's probably less of an issue. So, and because of that, the extinction is going to be physiology dependent. So there's differences, right? Not everything was affected the same amount, right? So marine species were more severely hit than freshwater and terrestrial species. Surface dwelling marine species were hit harder than deep dwelling marine species, right? But you kind of you're kind of removed from the most immediate effects of this. Of course, detritus feeding organisms are hit less drastically than those with other feeding strategies, because you don't rely on that food chain. If you rely on the food chain, especially with primary productivity like really being diminished after the impact, you're gonna have a problem. And then, of course, the organisms that could shelter underground are just hit less severely than those that could not shelter. So I think this is a kind of good thing to keep in mind as we kind of like step further back in time, how, again, different species are going to be affected differently. And one part of that is, of course, the complexity. So yeah, just to wrap this up, right, of course, the KPG boundary, the impact event, marks the end of the dinosaurs, which we don't care about dinosaurs, that's fine. Maybe we care about mammals. So, I always joke that the KPG boundary, the impact event, was maybe the best thing that could have happened to us. Because without that impact event, we probably wouldn't be here. Maybe there would be just like dinosaurs still roaming around. And we can see here that, mammals started evolving before the KPG boundary. And there was certainly like some reduction like in the mammals with the impact event. But you can see afterwards, because we are vacating these niches, we see this big radiation in mammals, which is great for us. But again, it doesn't matter for us in astrobiology, because what we really care about is microbes, right? So how did microbes recover from the impact event? So I was already saying earlier, right? So you have got the impact event here, you have this huge tsunami kind of swashing around. And then initially you're going to have kind of this melt sheet at the site, so that's not very good for microbes. But if we know anything about microbes, they tend to be quite hardy. Just think about how much effort is being put into like sterilizing all of those satellites and like an equipment that they're shooting to the moon. So it seems that, after the impact event, once things started calming down, so let's say after a few years to decades, right, and maybe more than that, but once kind of the melt sheet started cooling down enough that you were able to have water here again, it seems that, with the tsunami kind of having washed around, a lot of detrital material was able to go like into the crater site. And it seems like there was a bloom in cyanobacteria, like pretty shortly after the impact event. So you've got this here, days to years to 30,000 years here, we've got this bloom of cyanobacteria. And then if we wait a little bit longer, we are starting to see periodic euxenia, and we start seeing more sulfur bacteria. So, that's not too bad for microbes, right? Doesn't look like a mass extinction. We can also look at this more globally. So this site over here, this is the crater site, but what on a more global scale? So this has been modeled, and of course, when we look at the net primary productivity over here, so here we're looking at time after the impact. So after zero, there's a strong decline in the net primary productivity. But then they're modeling here, it looks like there might have been actually a spike in primary productivity. And this is coming from, the impact. You've got all of the dust that is being ejected out. And so you're actually putting a lot of iron and phosphorus and other material like on a global scale all across the globe. So this might have actually allowed for a bloom, right? So an increase in primary productivity that would have lasted, for several decades. So, thinking about the KPG boundary, we think of it as being really disastrous for life. But when we kind of apply what we learned from the KPG boundary to deeper time, there's actually some good reasons for optimism, that these impacts were not just destructive and caused mass extinction, but that they might actually have helped the early evolution of life. So this is bringing me to early Earth impact events. So as I was mentioning this morning, right, so there's not a lot of Archean crust preserved around the globe, but there's some Archean crust preserved. And there's some places that are really excellently preserved where, the rocks only reached 300, 350 degrees Celsius, so that we actually can still look at the sedimentary rocks to understand the early impact history and the effect on life. So the two great places here are the Kapwal Craton and the Pilbara Craton, where altogether about evidence for at least 15 impact events have been identified. And there's more and more that people are finding now that we are that we know what we are looking for. And And when we kind of want to understand the early Earth and the Hadean, for example, how impacts might have affected the early evolution of life, so whether it's on Earth or maybe on other planets, we might want to do some modeling, but we really want to root it in like actual observations from the Archean, where we know what happened, how it affected it, to kind of like ground truth our models. And then, of course, other things that people do are modern analog studies here and experimental work. So these two areas here are kind of the most exciting areas where most of the early impact record has been identified. So that's in the eastern Pilbara granite greenstone terrain here, and then in the Kapwa Craton in the Barberton greenstone belt. So, and I'm going to particularly highlight the Barberton greenstone belt. So the Barberton greenstone belt is located here in northeastern South Africa at the border to Eswatini. And this area really contains the richest record of the early impact history. I think essentially it just means that this is where people have looked the most. Probably if we spend some more time in the Pilbara Craton, we'll find an equal number or like more evidence for impact events. So in total, 8 impact events have been identified. So looking at the stratigraphic column here, so the Barberton greenstone belt contains rocks between 3.55 and 3.2 billion years ago. And here we've got 8 impacts that have been found where we have at least one major impact, so the size of the Chicxulub impact, or larger, about every 15 million years. So when you compare that to the impact flux today, we would expect an impact like this once every 500 million or a billion years. So much, much higher impact rate here. Again, and I think the sample is going around right now. So mostly these have been initially identified by these spheral beds here, and then been confirmed by iridium anomalies and chromium isotope signatures. And here we're looking at the chromium isotope signatures. I don't want to go into too much detail, but what's important here is that all terrestrial rocks are sort of going to follow by definition, like they're going to plot at 0 here. And when we've got extraterrestrial materials, so we might be either more negative and positive. And you can see in the study from 2003, they're looking at the S2, S3, and S4 impact events. They show negative values, and those are interpreted to reflect evidence for that the bolides, the impactors, were carbonaceous chondrites, which is going to become important later in the story. All right, now, so how big were these impacts? So again, just for comparison, the KPG boundary distal impact layer is about 1 centimeter or less. So these impact layers, many of them are like 15 centimeters, right? So in the impactor size, the sphere bed thickness scales with the impactor size. So we can use that information to kind of back calculate how big the impactors were. And you can see here for the Paleoarchean, the impactors were between 30 and 70 kilometers in diameter. So much, much bigger than the Chicxulub impact. And then for the Neo-Archean impact events, so those that we are looking at here, we're still looking at impacts between 6 and 50 kilometers in diameter. So huge impactors, in some places really well preserved so that we can look at them in more detail. And, just taking this up front, it's really interesting how, like in the scientific community, the thinking has shifted. So initially, and I hope this is something you'll take away after this talk. If you forget everything else, just take this away. And it's just simply that, we tend to think of impacts as being disastrous to life. And there was this famous paper by Norm Sleep on the annihilation of ecosystems by large asteroid impacts on early Earth. So initially I thought, okay, these impacts might be sterilizing, right? But then there was a follow-up study by Abramov and Moschitz. They are modeling these impactors, and they are saying, well, even if there would have been a late heavy bombardment, there would have been enough refugia left for life to survive. And now what's been really interesting to see that there's more and more studies coming out talking about the role of meteorite impacts in the origin of life in a more positive way, right? How could it have enhanced the origin of life? All right, so before I start showing you a whole bunch of pictures of the rocks, we first kind of need to anchor ourselves, because as I was saying earlier, the effects of giant meteorite impacts are going to depend on the conditions in the life that's present at the time, right? If the conditions are different, the effects of the impacts are going to be different. So something that we learned from this morning, or from the rock record in general, right? So the early Earth was likely a water world with little crust emerging above sea level. So even in Archean rocks, where we actually have a sedimentary rock record, most of those were water lane. So there was probably a little bit of emergent crust, but not too much. Mostly Earth seems to have been covered by water. Then when we look at the ocean composition, it was quite different. So one thing is that the oceans were enriched in iron. So iron 2 plus, which is the soluble iron. And one important nuance here is that, at least in the Barberton Greenstone Belt, during the deposition of those rocks, it seems like the lower oceans were enriched in iron 2 plus, the shallow oceans were depleted in iron 2 plus. It's going to become important later again. Then the other thing is, because we didn't have any like organisms that were building like silica skeletons or anything, so the oceans were really super saturated in terms of SiO2. Then in terms of the composition, right, in the Archean we had a really high PCO2 but really extremely low PO2. Again, you know, when we think about how impacts might be different in terms of how they affect the environment, right, if you have outgassing from an impact of CO2, if you're already in a high CO2 atmosphere, it's not going to matter that much. In terms of life, it was really simple prokaryotic single-cellular bacteria in Archaea. And another thing that's going to be important later on in this talk is that the rates of primary production were probably low, and it was either limited by nutrient availability, so for example, phosphorus, electron donors, or both. All right, so let's kind of talk through some of the effects of these giant impact events. So the first thing is that, you know, with all of the impact events that we see that have been found in the Archean, all of them are associated with some high energy current events that are usually interpreted as reflecting tsunamis. So imagine you have an impactor hitting the oceans, the early oceans, you know, you're displacing the entire water column. So you're going to create a tsunami that's bigger than anything that humans have seen. And there's plenty of evidence for that, again, in the rocks. So you can see over here, this is one of the Neo-Archean sphere layers. So it's this bed here, 2.45 billion years old, from the Hermes-Lay group. And here you see these symmetrical ripples, which reflect that oscillatory motion of the tsunami sweeping by. And then the S2 impact layer, and I'm going to be talking more about S2 later, but just to show you beforehand, so before the impact event here, we have got these black and white banded shirts, kind of suggesting calm energy conditions with abundant life. And then the spheroids are found in these high energy deposits, right, that have really big chunks of them in them. And these chunks are basically just like the ocean floor being kind of ripped up and transported along. So we see that as evidence for the tsunami sweeping by. And then we've got a 1 meter thick black chert layer above the impact event. And we don't only see that for the S2 impact event that happened 3.26 billion years ago, but for a lot of the other Paleoarchean impact events that are recorded in Barberton. And what we think this represents is that, you know, when you have got the tsunami wave coming through, like ripping up the seafloor, inundating coastlines, you know, that material is going to go up the coastlines, it's kind of wash back, so you've got the backwash deposits. And then you're bringing a lot of organic matter into suspension, and that stuff is really light. So it's going to take longer to settle out. So we think that basically all of this is a reflection of the tsunami deposit, but this is just like the coarser material that settled out first, and then you have got the slower settling of the lighter organic material and the dust from the impact, right, that's slowly settling out. So the other thing in terms of environmental consequences that we have evidence for is crustal fracturing. So these impacts, again, they're going to release really strong earthquakes that are going to travel across the globe. And here, this is again for the S2 impact. You know, the impact might have happened on the other side of the globe, so possibly quite far away. But what we see in many cases is that below the impact event, that there are these fractures that were then later filled with chert. And sometimes we see these masses of spheroids or individual spheroids in them. So the idea here is that you've got these impact earthquake waves that really greatly exceed the amplitudes of typical earthquake waves, much more extreme, and they last longer. And what will happen is if you have like lithified sediment, and cherts tend to lithify really quickly and they're really rigid. So if you have an earthquake going through, it's going to fracture and open up. So that's going to happen. And then at the same time, you know, you are liquefying the sediment, so the hydrated or water-saturated sediment that's like right at the seafloor, it's going to get liquefied and it's going to start moving. And we see a lot of infill of these chert dikes now with just like cherty material. So the other thing that's going to happen, and that also happened at the KPG boundary, but because the impact was small, it wasn't as disastrous. But when you have got the impact, you are just like converting a lot of like energy like into heat. So you have got, the melt sheet right at the impact site, but you also have the really hot rock vapor cloud that's expanding, at insane speeds, and it's going to cause a lot of heat radiation at the surface of the Earth. So when you have a giant impact, so impacts more than 440 kilometers in diameter, you are releasing so much heat that you would boil off the entire oceans. Like everything's gone. So that's, I mentioned this paper already earlier. This was the reason why they suggested that this caused the annihilation of ecosystems by large impacts. If you have a meteorite 190 kilometers in diameter, you at least boil off the photic zone. So it's really quite dramatic. So you can really see this nicely here. This was a later paper by Segura et al. In 2014. So here you're looking at time after impact, and here you're just looking at the temperature. And what you can see is that the temperature of the atmosphere goes so hot, right? You're above the boiling point for water, so your ocean waters really start boiling off. And you can see this here for this type of impact. You're starting to evaporate meters to tens of meters of ocean water. What this does is, right, you create a steam atmosphere and then you're leaving behind a brine. And, not only does it get hot, but then you also have to deal with the brine, right, if you're an early microbe. So those would all be stressors on the early biosphere. Again, I'm a geologist, so I'm like, I only believe your models if I can see it in the rocks, right? And there's evidence for this in the rock record. So this here is from the S8 impact event. And what you're finding here right above the spheroidal bed, so the impact layer, is these curious silica crusts. And these are thought to have formed from partial ocean evaporation. So again, you're not evaporating the entire ocean, but maybe the uppermost few meters to tens of meters. So, and because the oceans were super saturated and with respect to silica, you start forming these silica crusts. So actually, David, who is right over there, he's working on those silica crusts, trying to understand their formation a little bit better and trying to see if there's any evidence for life in those crusts. And then another evidence for this partial ocean evaporation is in the form of pseudomorphs. So the rocks are really ancient. There has been a lot of replacement, but we do find these really curious crystals, the euhedral, right above the deposition of the tsunami layer, so right where we would expect, evaporation to be the highest. And we think that we started forming these salts from the partial evaporation of the oceans. So this is all consistent with, you've got impact events big enough to, heat up the atmosphere so hot that, any life on land, for example, would probably be gone, at least if you're surface, right, like at the surface. But now it kind of begs the question, okay, even if we have the highest impact flux, does it really mean that we are annihilating all of life? Right, so and this is the study I mentioned earlier by Abramov and Moschitz in 2010. So they did some modeling, and they were modeling the late heavy bombardment when we still believed it was there. But it doesn't even matter, right? Because the impact flux was higher in the Hadean, so you can just use it as a beautiful Hadean example. And they are looking at, okay, if we have this high impact flux, what is the temperature of the crust? What temperature does the crust reach, right? And there's a lot of temperatures here that life just couldn't survive, but in blue here is anything lower than 110 degrees Celsius, where at least some life could survive. And the model, even like with the most extreme impact flux here, you can see at the surface of the Earth, there's plenty of crust left that is 110 degrees or lower. So any life that maybe wasn't at the surface in contact with the atmosphere, where things really started heating up, but maybe a little bit in the subsurface, that type of life would have survived. And it's also one of those arguments, right, when you think about LUCA, that maybe these impacts were some sort of bottleneck, right? You form life, you have it evolve, you have giant impacts that really heats things up, and maybe only hyperthermophiles were able to make it through that early impact flux. The other thing we can think about is the phosphorus contribution. So these impacts might have actually delivered quite a bit of phosphorus to the early Earth. So phosphorus is a bioessential element, and I was already mentioning earlier, right, that the early oceans were probably starved in terms of phosphorus. In part is because we need, phosphorus, when it's being released kind of from the abiotic Earth to the biotic Earth, it's mostly the riverine flux that's coming off the continents that's flushing phosphorus into the oceans. If we don't have a lot of land masses, we are not flushing a lot of phosphorus into the oceans. with these impacts, we are putting in not only just phosphorus, but really reactive, reduced oxidation state phosphorus that is much more bioavailable. So that includes minerals like schreibersite. So this would have really been important for the early biosphere. And you can see in this work here by Walton et al. In 2023 how the phosphorus flux might have kind of mirrored the impact flux throughout Earth history. And it also kind of has some reminiscence of earlier. I was showing you this graph how there might have been a peak in primary productivity. So that because of like phosphorus delivery, but in their case also they're talking a lot about iron delivery into the ocean. So, impacts also have a positive side here. And we do see this in the rocks. So this is again from the S2 impact layer. And here we can see the samples below the S2 spheroid bed, so it's relatively low phosphorus content. And then look at here, these are the samples from the spheroid bed. How enriched they are, like in phosphorus in comparison to what we had before. So it looks like there was quite a bit of phosphorus contribution. There's still higher phosphorus, like slightly elevated phosphorus after, but it seems that most of the phosphorus might have come just from the impact event, from the impact deposits. And then the last thing I want to talk about before I switch to directly talking about the effects on Archean life is that there's a number of impact events, so at least 4, where people have described an increase in iron across the impact event. So this is the paper that we published just last year. So this is the iron content before the impact event, so it's relatively low. And this is really in agreement with, at that time, we had this ocean where we had the iron-enriched deeper ocean and the iron-depleted shallow ocean. So here we are in shallow water, so we have really low iron. And then with the impact event, we see this really strong increase in iron. It kind of peaks over here and then slowly starts declining again. Again, it hasn't only been observed from the S2 impact, but a number of different impacts. And it has been related to different things. So it might be that the impact caused big tectonic changes that caused deepening. So we are kind of passing through the chemoclimate into deeper waters, and that's why we see the increase in iron. It might be that the impact triggered uplift and weathering of mafic crust, or it might have triggered volcanic and hydrothermal activity, right? All of those are reasonable. Some of that has been modeled. And then lastly, it's possible that, right, just with the passage of the tsunami, you might have mixed the oceans really well and brought that iron-enriched deep water to the surface. So for the S2 impact event, we tested for all of these different possibilities, and we think that ocean mixing, at least in this case, is the most parsimonious explanation, which doesn't mean that these other things are not happening, right? It doesn't mean that you might have some uplift associated with the impact or hydrothermal activity, especially close to the crater side. But at least for the S2 impact event, it seems like the major cause for the increase in iron was the ocean mixing. So now I want to talk a little bit more about how did life react to that. And not a lot of work has been done on this, but we, again, published a study last year looking at the S2 impact event and trying to see, okay, how did the environment and life evolve like across the impact event? So again, this impact happened 3.26 billion years ago, and the bolide size was between 37 and 58 kilometers in diameter. So here's just for comparison, the Chicxulub bolide, about 10 kilometers in diameter. And here in comparison, this is the lower estimate for S2. So, and again, so what matters, to some extent is the diameter, but really the mass is what the effects are going to scale with. So in terms of mass, it was 50 to 200 times bigger than the KPG impact. So yeah, this is the paper that we published, and I'm not going to spend time too much on the environmental consequences because I was basically showing them to you already. But just to summarize, right, before the impact event, we have got the iron-enriched deep water and then the shallow water. There's some life present, but not a whole lot. Then the impact occurs, and we see evidence for that huge tsunami really kind of passing by, mixing up the waters, ripping up the seafloor, inundating coastlines, being really dramatic. And also causing turbid conditions, right? So not only are you putting a lot of dust into the atmosphere, but you have really turbid conditions in your water, so that even if you did have sunlight, it couldn't penetrate. And then other environmental effects that we have evidence for is, again, the heating. So we see these salts that formed right after the impact event, so these evaporites that we think are from partial ocean evaporation. And this has some really important consequences because, at least for a short time, if you're heating things up and you're putting a lot of steam into the atmosphere, you're going to increase weathering and erosion, which might increase your nutrient flux into your environment. And then the last thing, of course, bolide vaporization and dust emission, which caused initial darkness and injection of phosphorus and iron. So those were the environmental consequences. So, what was the effect on life? So the first thing that we looked for is, so we did carbon isotopes of the entire sequence. And the first thing we were basically looking for is there any negative shift in the carbon isotopes? So I was mentioning at the KPG boundary, you've got the collapse of primary productivity, and that's kind of the collapse of the carbon pump or the biological pump in the oceans, and that caused the negative trend. So you can imagine, right, so the oceans today, because you have a lot of life in the surface waters, so all of that life really likes the light carbon isotopes. That means that the remaining water in the dissolved inorganic carbon reservoir is going to be relatively heavy. And then as you go deeper, you kind of get close to zero. So do we see any evidence for that, was the question. So here we are looking at carbon isotopes here, just from the interval right above the impact event. And I always say, right, if you have a few beers and you squint your eyes, maybe you can see a trend, right? It's not a strong trend, like the R-square is like 0.41, and let's not look at that number, but let's just assume it's there, right? Let's assume it's there. We actually don't think that this would reflect, mass mortality. So the first thing is that, during the Archean, there was life, surely, but the primary productivity was not as high as today. So you wouldn't even have that carbon isotope gradient that would collapse. So even if you had mass mortality, like you wouldn't see it because, probably you would, throughout the water column, you would have values just closer to zero. And then the other thing is that when we look at the carbon isotopes, that correlate somewhat nicely with the grain size. So here in red, I'm plotting the maximum grain size versus the carbon isotopes. So you can see they have similar slopes. So what we think is more likely to have happened is that, again, you have the tsunami rushing through. You've got all that organic matter that's kind of being mixed up and homogenized in the water column, and that starts raining out. And with organic matter, and we see that in modern settings, is that sometimes, depending on the organic matter sources, the larger organic matter particles are going to have a different isotopic signature than the smaller ones. So we think that this is what we may be seeing here. So we don't think, oh, well, it's this, and maybe the biosphere just kicked right back in, and we are just seeing mixing with concurrent carbon production. So even if you were to believe that this negative trend is real, we don't have good evidence that this necessarily reflects mass mortality. We can look at the just total organic carbon content, right? Maybe we see a huge peak in the organic carbon, and that's just like all of those microbes that died and kind of settled out. And there's some increase in the TOC. So here looking at TOC kind of through time. Should have said this earlier, but in stratigraphy, right, we're looking at the older rocks at the base and we younger here. So you can see right after the impact, we see these high TOC values, but they're not necessarily unusual. So you've got an interval further down here where we have similarly high TOC values. So it's not something unusual that we see associated with the impact event. So this makes us think that at least within the rocks that we are looking at here and at the sampling resolution that we have, we don't see any clear evidence for mass mortality. That doesn't mean it's not there. Right? If you're stopping photosynthesis, if you heat things up, or if you're mixing things up, like of course there would have been mass mortality. But we think that's a possibility that just life, bounced back so quickly that, we just don't have good enough resolution in our rocks to see that. Right? Sedimentation rates tend to be really quite slow, so to capture an event that only lasted a few years can be really tricky. So is there any evidence for a positive effect on life? And here we're really testing the hypothesis if the increase in phosphorus and iron might have allowed for microbial blooms. So probably after the impact, there's a lot of things happening, a lot of different chemistry. But like amongst all of that, do we see any evidence for microbial ion cycling? And what we are looking for is, the presence of life, but then also the metabolic byproducts, right? So in microbial ion cycling, you have got iron 2+, which is soluble, right? This is used by photoferrotrophy, and in the process, it gets oxidized to iron 3+. Iron 3+ is insoluble, so it's going to start forming ferric oxyhydroxides that are just going to sink down the water column and kind of settle on the sea floor. And during the sinking, or once it's on the sea floor, it's going to be used up by desalinatory ion reduction. So in this process, we kind of like using organic matter for metabolism and releasing CO2 and iron 2+. And this process is a really strong alkalinity pump. So that means it's going to trigger carbonate precipitation. So we start seeing siderites over here. So that's an iron carbonate. Not only should we be seeing siderites, but the siderite should have a characteristic carbon isotope signature, because again, you're losing, remineralizing like organic matter, so the carbon is going to be depleted that's used in this process. So the siderite here should not have the carbon isotopic signature of the seawater, but kind of should have this isotopic memory of the organic matter that was used during dissimilatory ion reduction. So we do think that we see evidence for this happening. So here's the whole kind of section with the carbon isotopes. And at first we were really confused by it, right? So just to anchor you again, so here's the fallback layer that I was showing about, with a possible negative trend. But when we look at the whole section of carbon isotopes, before the impact event, it's really variable. It's quite light, right? So you have a lot of organic matter with a light signature, good evidence that there was life around, but it's just kind of wiggling back and forth. And this is not like atypical for Archean charts. So this is, quite common that we see that. And what exactly that means in terms of what metabolisms were present is kind of hard to say. And that's the thing with the KPG boundary, we can look at bones and like all of these biomineralizing fossils. So it's really easy to see what the effect on life was. So here in the Archean, it's a little more tricky. But how this is often interpreted is that you have some kind of primary productivity, maybe some form of photosynthesis or something, and then that material gets kind of reworked, recycled by other processes, so methanogenesis, methanotrophy, all of that, and that's why you see so much variability here. So now, after the impact event, like at first, we really a little bit confused as to what we are seeing. So you can see in the Brewster's Hill section, the data looks essentially bimodal after the impact. In the Umba section, we don't see that bimodality, but we kind of see, a sort of a shift to like a little values that are much more homogeneous and a little bit heavier in the carbon isotopic signature. So let's just take this apart a little bit more. And the first thing that I hope to convince you of is that there's some kind of association between the shift in carbon isotopes and the increase in iron. So when I use this data and now I color it based on how much iron is in the samples, you can see that if we only look at samples that are high in iron and low in aluminum, we get these like really homogeneous values, this really narrow spread, and they're relatively heavy. If we look at other samples in the Brewster's Hill section, you can see this bimodality is clearly defined by the lighter samples having more aluminum. And what we think is happening is that, the aluminum is a really good proxy for sediment input. So, if you are kind of reworking older sediments, so like older organic material, then you're going to see an increase in aluminum in your samples. So we think that those lighter values here are just a reflection basically of organic matter that was deposited before and reworked. So if you want to see like a really pure signature of what life was doing at the time, we want to kind of like forget about the stuff that's like old and being reworked, but we want to kind of see what's happening at the seafloor right there. And that's what we are looking at here. So we see the carbon isotopes that are high in iron that are relatively heavy and like much more homogeneous signature. So this is some indication that, the carbon cycle reacted to the increase in iron, and especially since, carbon was like abundantly available, it's very likely that the shift in carbon isotope is telling us something about predominant metabolism shifting. So it doesn't mean that there's only one metabolism happening, but maybe there's a shift in metabolism and there's now one that's much more predominant. So the second thing that's important is that those samples are just full of siderite. So I was mentioning earlier that siderite is one of these important byproducts from microbial ion cycling. And this is important because siderite precipitation, even after meteorite impacts, is really inhibited under Archean conditions. So you can't just form it in the water column and then that rains out, but it's kinetically really difficult to do. So when we look at the samples in a little more detail, we see here for the siderite, the siderite oftentimes clusters around organic matter. So this dark cloudy stuff here is organic matter, and it's clearly associated with lots of siderite here. It's really covered in it, kind of suggesting that it's the siderite is diagenetic in origin again. So it formed in the within the sediment itself. So not only do we see siderite, but the other byproduct of this microbial ion cycling that I was mentioning earlier is iron oxides. So, so hematite, magnetite, and that's what we are seeing in quite a few samples here. So here this cloudy stuff is the organic matter, and then you see all of these grains. So the larger, darker ones here are magnetite, and the lighter, smaller, redder ones here are hematite. So we've got all of those things kind of together, like at the same place, which would be consistent with microbial ion cycling. We still weren't fully convinced, so we took it a step further, and we looked at the siderite itself, like within our samples, because if this truly is from microbial ion cycling, then we should see that isotopic memory of the organic matter that was being reworked. So do these siderites have that negative and variable carbon isotopic signature? And they do. So here we are looking at the carbon isotopes of the carbonate this time. And you can see that the carbon isotopes are like fairly negative and really quite variable. And that's like a good indication that we're looking at like kind of pore water processes, and that we are using some of that carbon from the previous organic matter. One caveat to some extent here is that to really use this to make a strong argument, we need to have a strong control on what the background carbon isotope signature was. So what was the carbon isotope signature of the dissolved inorganic carbon? And we don't have any carbonates like right from rocks the same age, but we have carbonates from like immediately below. So there's like within the comediates, there are these fractures that are filled with carbonate. There's other carbonates like of similar age, in other places in the Barberton Greenstone Belt and in the Pilbara, and all of the data centers around 0 per mil. So we think this tells us that the carbonate is coming from the dissimilatory ion reduction. So putting this all together, so we have got 3 lines of evidence here suggesting that there was microbial ion cycling. So at least the data is consistent with microbial ion cycling. Again, I'm not saying that this is the only thing that's happening, right? Probably after an impact like this, we are mixing stuff, we are heating things up. There's a whole bunch of different chemistry happening. But we do think based on the shift in the carbon isotopes, the presence of iron 2 and iron 3 plus minerals with organic matter, and the light and variable delta 13C carbonate values is providing some indication that there might have been really active microbial ion cycling. So we picture kind of after the impact a world like this, where we have iron now mixed throughout the water column. We have abundant microbial ion cycling and potentially really mass blooms, because now we've got all these nutrients and electron donors widely available. So what was the effect on life? So it really goes both ways. There was likely really short-lived decimation of phototrophs living in the photic zone. But when it comes to other organisms, so chemoautotrophs that, for example, are living lower in the water column, or hyperthermophytes, they likely would have been just much less influenced. And we think that that probably lasted for as long as the conditions were bad, so a few years to maybe decades, which geologically speaking is a very short amount of time. And then once conditions return back to normal here, we think that there might have been really mass blooms, especially of microbial ion cyclers. All right, let me just see. Okay, so I have a little bit of time. So I'm going to briefly talk about impact events and the origin of life. Right, so now we are stepping even further back into the Hadean and trying to see how impacts might have facilitated the origin, the early evolution of life. And there's a number of things. So first, of course, there's the delivery of compounds, right? There's the famous idea of panspermia. So maybe life was delivered by a meteorite to Earth. And, it's really, extraterrestrial life, like somehow survived the flight and then like landed on Earth and was able to proliferate. But even if you don't buy into this, right, when you have these meteorites, I was already talking about the release of nutrients such as phosphorus, potentially iron. But, if you consider all meteorite classes, a total of about 80 different amino acids have been reported. So these might have really helped the origin of life. So here, for example, we have got the Murchison meteorite here, and that contained over a dozen amino acids, including glycine, alanine, and glutamic acid. The other thing, and especially a lot of the chemists that think about the origin of life and chemistry for the origin of life, they're really like hydrogen cyanide. So it's got hydrogen, carbon, nitrogen, and all of it in a reduced state, which is kind of like what we need for life. And when we think about the Hadean Earth, I was already saying earlier, based on the information we have from the zircons and outgassing, the atmosphere was probably rich in CO2 and nitrogen, SO2, so it wasn't that reducing, which is a problem, because if you want to form hydrogen cyanide, you need really quite reducing conditions. And you can achieve that with a meteorite. So if you have a meteorite or an asteroid, especially with an iron core, you start creating more reducing conditions. So here in phase 1, the impact vaporizes the ocean, and hydrogen is generated by reactions between the atmosphere and impactor iron and the melted crust. So this will happen within days to months here. And then in the phase 2, as the steam cools, equilibration between hydrogen, nitrogen, and CO2 makes methane. And NH3. So, that material is going to eventually condense, and this is when you start forming hydrogen cyanide. So you can see this in this graph here. So here's like the abundance and time after the impact. So here you can see the hydrogen cyanide like forming and raining out. So although, the atmosphere was not very reducing during the Hadean, there might have been these relatively short intervals after giant impacts where you might have had a reducing atmosphere to generate some of that hydrogen cyanide. One of the last things I want to mention is that, with the impact events, even at the site of the impact, where I was saying earlier, well, those might have been disastrous because you form that melt, right? So here we're looking at a complex crater. So we've got our impact melt here, and you had the shock waves that were, radiating outwards. And like as an effect, you're really shattering the crust. Yeah, you're increasing porosity and permeability, and you're creating heat. And this, although initially, the impact might have been disastrous for life, it actually creates conditions that are interesting in terms of prebiotic chemistry, but also in terms of early habitats. Hydrothermal vents are really commonly associated with impact events. So here we are looking at a map of impact craters. Again, there's this geographical bias with North America and Europe. But in all of these impact craters, there's been evidence for hydrothermal systems developing after the impact. This has become more and more interesting, and especially in the last couple of years, there have been a few papers on the Chicxulub crater, but also the Fredefort crater. So here's just the example of the Chicxulub crater, where Simone Marchi did some modeling here, and he's just modeling the impact event and how that affects the porosity and permeability. And you can see, so here's the crater, you're moving away from the crater, how you're really increasing porosity and permeability close to the crater. And then, of course, you have got the heat, right? There's a thermal anomaly associated with the impact event, and that allowed for hydrothermal cycling here. And that's what you're seeing here. So you've got the colder waters kind of coming in. This is where it's going to be hotter, that hot water rises, and you kind of form this hydrothermal circulation. And those environments might have been like really interesting for early microbes. So here you can see from the Chicxulub crater some evidence from the drill core that they took there recently of these hydrothermal channels, and they found within those hydrothermal like systems, they now have been doing work on like sulfur isotopes, and they have found evidence for microbial sulfur activity basically happening in this hydrothermal system. So there's a lot of environments that you're creating in this impact event with a hydrothermal system that's interesting in terms of prebiotic chemistry. And, I'm not a prebiotic chemist, so other people might be able to speak much more to this. But, one thing that's happening is that, you've got this impact and you've got some uplift here, especially during the early Earth where the crust was probably a little more mafic. So you might be uplifting kind of like oceanic crust or basaltic crust to the surface. And when you have hydrothermal circulation there, you start seeing serpentinization, which releases hydrogen. So that's a really important environment for the origin of life that has been proposed for a long time. So that, in marine environments, but I was saying earlier that terrestrial environments have become much more interesting for origins of life scenarios, right? So of course, when you have an impact, if it's in the deep water or on land, and like in both of those settings, you can create these hydrothermal systems that might be amenable for prebiotic chemistry. And then you've got other things, that are less commonly cited, but volcanic splash pools, hydrothermal sedimentary contexts, or pumice rafts that have been proposed as possible sites for the origin of life. So as such, these are possibly locations that might be interesting to think about for the origin of life and, the early evolution of life. Again, there's some evidence for microbial habitation in these hydrothermal systems. So with that, I'm at time. Great. So if anything, like I want you to keep in mind, because we think of impacts as being really disastrous, and the first thing that people think is like, oh, the KPG boundary, mass extinction, all the dinosaurs went extinct. But even at the KPG boundary, like microbes recovered remarkably quickly. And as kind of astrobiologists, what I want you to take away is, yes, these impacts were disastrous in many different ways, but they also really inferred some potentially really important benefits, and that includes, right, the delivery of material, right, amino acids live through the bolides themselves. Then you've got these more proximal effects, right? You generate new habitats, you potentially generate conditions that are more favorable for prebiotic chemistry, and you may be generating the chemical and mineral ingredients for life. So, that's happening. And then at the same time, even if you're really far away from the impact site, right, as I was showing from our 2024 study, we do see good evidence for an injection of nutrients, right? We see this increase in phosphorus, potentially iron, and we have some evidence for the mixing of the ocean, which might have also brought more nutrients to the surface. So for that, even if you forget everything, just impacts are really double-edged sword. They're good things and bad things. And with that, thank you so much for your time.